So hello together. Today I want to talk about special devices which we will need to set up certain circuits for or to realize a certain measurement equipment. And of course, if we want to realize a measurement equipment, we need first a generator, or better I say a signal generator. And here I gave the picture of the symbol of a signal generator, and if I consider now transmission line theory, it looks like this, that we have a certain transmission line here with a characteristic impedance ZC, and to this transmission line is connected a voltage source with an internal resistance ZG, and of course this ZG, if this is not identical to the characteristic impedance of the transmission line, this will result in an RG in the signal flow graph of this, and of course the voltage source U0 will be responsible for the wave amplitude A0, which will be generated, and this is fed to this output port A1. So this is the overall signal flow graph of a signal generator, or as I said here, just a generator. And the next very important point, we need a so-called absorber. And an absorber is, if a wave enters into an absorber, then the wave will be, the energy of the wave will be converted to heat. And if I have an equivalent circuit for a transmission line, then it behaves like this. We have a transmission line with a characteristic impedance ZC, and this transmission line with a characteristic impedance ZC is terminated in its characteristic impedance ZC. So as a result, in the ideal case, we will have that the S parameter S11 of an absorber is 0. And of course, we can do the following. We can assume that this absorber is equipped like this, that I can measure, for example, A1, and I put here a measurement equipment, and I say this measured the wave amplitude A1. How this can be realized, we must talk in a later lecture. And also what we need to set up a measurement system is a so-called isolator. And the isolator is responsible for the fact that if a wave is reflected back into our generator, this wave will be absorbed in the isolator. So the signal flow graph of an ideal isolator looks like this, that a wave which will enter into the isolator will essentially go through. Of course, there will be a phase change, but this is not of interest at the moment. But as soon as a wave will be reflected or will enter into the isolator from the wrong direction, then it will be absorbed in the isolator. And here I sketched how, for example, an isolator can be realized with the help of a circulator, but unfortunately we did not talk about the circulator now. But a circulator works like this. If a wave enters into the circulator, it will emit the wave from port 2, for example, and if a wave enters into port 2, then it will come out of port 3, and here the wave will be absorbed again. So no wave will come back to port A if a wave is reflected into port 2. So these are the first essential elements we need to set up our measurement equipment, and in the next step I will talk about the most important device for measuring, for example, S parameter, and this is the so-called directional coupler. So at the moment we are preparing to set up a measurement system to measure the S parameters, and the most important element to measure the wave, the S parameters, is a so-called directional coupler. And the directional coupler is a so-called 4-port, and in our case we consider here a waveguide coupler, and it's like this, that we have here port 1, port 2, port 3 and port 4. And if I insert a wave into port 1, the essential wave will go through to port 2, but a part of the wave will be coupled to port 3. And the same is true, for example, for port 4, or the equivalent is true for port 4. If I insert a wave into port 4, the essential part will come out of port 3, but a small part of the wave will be coupled to port 2. So in the ideal case, a directional coupler will be described by two scattering parameters, which we call the transmission coefficient and the coupling coefficient. I sketched here the scattering matrix for our one port, and to start to fill in the scattering parameter, we can say, since these are two waveguides which are essentially not disturbed, all elements of self-reflection will be 0. So these elements will be 0. And of course now we insert first the transmission parameter. So we have a transmission, for example, from port 2 to port 1, and also from port 1 to port 2. And we will have a transmission from port 4 to port 3. And also we will have a transmission from port 3 to port 4. So these are the transmission coefficient, and now we account for the coupling coefficient. So we have a coupling, for example, from port 3 to port 1. Here we have the coupling, and also we will have a coupling from port 1 to port 3. And so we will have a coupling from port 2 to port 4, or from port 4 to port 2. Here we have a coupling, and also we will have a coupling from port 2 to port 4. So these are the essential coupling coefficients, and very important also are the isolation. And we will have, for example, no coupling from port 1 to port 4, which is normally called the isolation. And we can here insert a 0, here insert a 0, here and here. So this is essentially the scattering matrix of an ideal directional coupler. And as you remember, we also did discuss in the lecture already the absolute value condition, and according to the absolute value condition, we have that the sum of the absolute value square of a Coulomb must be 1. So we have the equation that T absolute value square plus C absolute value square must be 1. Or we can say, for example, that solve for example for T, that the absolute value of T will be equal to 1 minus absolute value of C square, which means that the power which will be coupled from the waveguide, of course, will be missing for the transmission coefficient, its absolute value. What I want to do now is I want to discuss the principle of operation. So essentially, if I have a directional coupler built up of waveguides, so these waveguides are essentially soldered on each other, and the simplest form of a directional coupler can be constructed with two holes. So a coupling will result through the two holes, and the essential point now is that these two holes are a quarter wavelengths apart of each other. So we have here the wave propagation. As you know, wave propagation is described by beta as 2 pi over lambda, where lambda means the wavelengths in our waveguide. And so the transmission coefficient, for example, I inserted here some wave amplitudes, and we will have a transmission from here to here, which will be essentially equal to minus j beta L, where L is the distance of the two holes, and this will result in a phase shift of 90 degrees. And now we can, in principle, distinguish two different cases. First I want to discuss the case 1. In the case 1, I assume that I have a wave amplitude A1. Of course, part of the wave amplitude will be coupled into into our waveguide, which I described by epsilon, and then in this case a wave will travel along this distance, and again here we will have t as a transmission factor, which is essentially 1. And here we have again the wave amplitude B1, also a part of the wave amplitude will be coupled and they will add in B3, but since the two transmission factors point in the same direction, we will get the same phase shift here, and we will get that B3 is proportional this expression. This means now that we have a certain coupling to port 3. If I now consider the case 2, in the case 2 we also have this transmission factor here, and the coupling through the holes, but in this case the wave will travel into this direction. So we will have that B4 will be proportional to the coupling and 1, but here we have the exponential function minus j pi, because they both will multiply to each other, and as you know, if I have an exponential function of minus j phi, then of course this is essentially minus 1, so that there will exist no coupling to port 4. So in the ideal case, port 4 will be decoupled from port 1. And in the next lecture we will see how to use these elements to set up a so-called reflectometer.